Hello again, everyone. We are going to discuss section 12.7 today, which is titled A Model for Chemical Kinetics. So we're going to look at other things that influence reaction rate versus concentration. So we know that concentration affects reaction rate, but what other things are involved? Well, we know that when we look at temperature, for example, the reason we use our fridge is because it decreases the rate at which food spoils. So lowering the temperature will decrease the rate. Wood burns or combusts at a very high temperature, so increasing the temperature increases the reaction rate. So we know that chemical reactions speed up when the temperature is increased, and we can see an exponential increase of the rate constant when this occurs. So this brings up a new type of model called the collision model, and it's based on the assumption that molecules must collide in order to react. And this also is partly explained by what we talked about in 12.6 with the molecularity and the collisions explaining concentration dependence, so number of species colliding, things like that. So now we're going to look at temperature dependence and how temperature affects rate of reaction. Okay, so if you go back to chapter 5, which talked about gases, the kinetic molecular theory says that an increase in temperature will increase the molecular velocity and frequency of collisions. If particles are moving faster, they're probably going to collide more often. Well, then, if increasing the temperature does increase collisions based on kinetic molecular theory, this would imply that reaction rate would also increase at a higher temperature based on our collision model. If we have more collisions at a higher temperature, then we have a higher reaction rate. Well, what we actually see is that the reaction rate is much smaller than the calculated collision frequency, so maybe it does speed up, but not as much as we would think. And the reason for this is because a small fraction of the collisions are actually producing a reaction and producing products. So we want to see, well, why does this occur? And so one of the theories has to do with activation energy. This is the threshold energy that must be overcome to produce a chemical reaction. And so if you take a look at the graph here, we've got our reactants starting here, and then we've got this kind of hump that things have to get over before we can produce products. Well, that difference is called the activation energy. And so we're going to talk a little bit about that. So let's take a look at this equation. Okay, and in order to take BrNO and produce bromine and nitrogen monoxide, we have to break the bonds between the bromine and the nitrogen. Well, breaking bonds involves a lot of energy, so we need energy in order to break those bonds and then produce products. So the minimum amount of energy that's required for those two BrNO molecules to get over the hill, so to speak, is called activation energy. And we use E sub A as our symbol. So that's when we talk about getting over the hill, we're talking about this part right here. This is considered our activation energy. And the energy to do that is furnished by the energy of collision, the energy when things collide together. So we know that if we increase the temperature, that means that we're going to increase the number of effective collisions. So not all collisions are going to result in products. We first of all need collisions that have an energy higher than the activation energy, because we have to get over that activation energy amount. So our collisions have to be high energy, or at least bigger than activation energy. So we can say that the number of collisions with an activation energy is equal to the total number of collisions times E to the negative E sub A, so negative activation energy, divided by R, which is our gas constant, times T, which is in Kelvin. So if we wanted to do an approximation for the number of collisions that are going to be above this activation energy, this is the equation that we can use. Total collisions times E to the negative E sub A over RT. Well, there's also something else that influences collisions. So even if we have a lot of collisions that have an energy that are above the activation energy, we found that the rate is still slow. So there's another factor that's involved here, and that's called molecular orientation. Molecules must be positioned correctly during a collision in order to actually react and produce products. They just can't randomly collide. And so here's an example of that. Some of the text isn't the best, but basically all of these collisions are called ineffective. Things are going to collide, but they're not going to produce products. We need to have this very specific orientation in order to get an effective collision, and then to actually produce products. So not all collisions are going to result in products. Okay, so based on these two requirements to form the products, which is the collision must have enough energy, so it must be either equal or greater than the activation energy, and we need to have a correct orientation, we can come up with a new rate constant. So here, K is equal to Z times P times e to the negative EA over RT. So this can be our equation for the new rate constant, where Z is equal to the collision frequency, and P is called the steric factor. It's always less than 1, and it refers to the fraction of collisions with effective orientations. And then our e to the negative EA over RT deals with the collisions having enough energy. So here is our orientation, and here's our bigger than E sub A value. Okay, well, we can rearrange this into what's called the Arrhenius equation. And so we have rate constant is equal to A times e to the negative E sub A over RT. So this A value is replacing the Z times P, which we're calling the frequency factor. We can also rearrange this equation by taking the natural log. And if we do this, we get an equation that follows the format y equals mx plus b. So natural log of k is our y. Negative E sub A over R is our m. 1 over t is our x. And natural log of A is b. And so we can plot this and get a straight line if we plot natural log of k versus 1 over t. And so if the rate constant follows the Arrhenius equation, a plot of these values will give a straight line. And then we can also use this to solve for A and E sub A. So considering that most rate constants do obey the Arrhenius equation, the collision model is really reasonable as far as how and why things are colliding and producing products. Okay, so we can also, like we said, we can use that plot to find A and E sub A, but there are other ways that we can find it as well. So we can measure K at several temperatures and then plot, get our straight line, and do all of that. But we can also calculate E sub A from values of K at 2 temperatures. And so if we take the equation from before and rearrange, we get this. So we have natural log of K2 over K1, so K at temperature 2, and K at temperature 1 is equal to E sub A over R times the quantity 1 over T1 minus 1 over T2. Okay, so we will go over some examples in class using those equations. Otherwise, here's the homework that you can get started on. Have a good day.